The first one is hardware software code design. Code design means how parallelly this can be designed. These are the major steps involved in the hardware software core design of the embedded system. First one is analyze the requirement. What all are the requirements for designing the system? Suppose you are going to design a thermostat. That is, read the temperature, check the temperature, compare the temperature with the existing room temperature. If it is fine, keep it as it is. Otherwise, switch on the cooler or the heater. Consider this is a small example. For this example, we will see how to collect the data and collect to implement this one. First step is the requirement and specification. What all are the requirement for the thermostat? Definitely, we need the thermosensor. So before doing this one, you should need something to know about the particular component. For each and every embedded system components, we should know what are the basic components required and how it can be connected. What are the coding part required to connect the different components, and you are only going to fabricate that particular board. So for this fabrication of the silicon board, how it can be designed in the board itself, when you see the board, there is only designs, no? So how can you design that one? That is also very very important. How will you find the path? There is a path. How to identify the path? What are the different tasks? What is the time period? That are all the things you should identify before you are doing your work.
நார்மலா போறதே பழக்கி
Mute your
அதுவும்
mic.
ரொம்ப பிடிக்கும்.
Vibhagaran, Vibhagaran, mute your mic. Okay, fine. In traditional embedded system design, the hardware software partitioning is performed at an early stage. Early stage it is partition and finally that is combined. But nowadays, before the partitioning itself, you should identify each and every component, each and every task, and then partition this one. So the traditional technique is entirely different from the today's technique. And in the hardware software core design, first functional requirements are collected from the user, and based the architecture is drawn. System has been drawn based on the functional requirements. So the exploration of the functional requirement is very very important here. That's crucial. You should identify the requirement of the system. What is the actual requirement? Based on the actual requirement only, the components will be purchased, and before that you go to the diagram. That diagram mapping is called as the architectural mapping. First identify the functions, and that functions are mapped with the architecture, and this stage is called as the architectural mapping. Then it is focused on after mapping, we should partition what are the hardwares required and what are the software, what are the coding required. For example, if you want to design a thermostat, that is our example. In our example, we need to read the sensor data, temperature sensor data. So definitely there must be a code to read the temperature sensor data. You should write a code, read this data from the port. This value should be connected with some port, and from that port you must read the value. For the port connection itself, you can use a microcontroller. No, in the microcontroller we are using the IO map concept. There are the memory map concept and IO map concept is there. We can use the IO map concept. Hence a separate code must be there based on the input. If you are going to get the input from the A port, from your port A, in your input contains two port A and B, and if you want to read the content from port A, then you should write the code such that read port A. Then only the contents are transferred from this port, that is the temperature sensor port, to your processor. Then your processor should process the information. Similarly, the temperature sensor can produce the temperature. That is one kind of analogous data that can be converted into your digital data. For that also the provision must be there in the microcontroller. After processing this one, we'll get the output temperature also, then that must also be displayed. For displaying that one, definitely we know the LED must also be connected with this microcontroller. Hence, first itself we should identify for the hardware components, how many ports are required. Based on the number of ports only you can purchase the microcontroller based on the requirement. So first one is the functions, identify the function. Second one is draw the architecture, how all these components are interconnected, and then partition it into hardware components as well as the software components. Then you implement the hardware separately and write the code separately. Hardware part is implemented for each and every task. The hardware part is implemented separately and the software part is implemented separately. After that, these two components are interconnected or integrated. Integration is the tedious work. There you can identify so many errors. When you're writing the code, it's fine. But when you try to integrate the code, it won't be working in a good manner or a efficient manner. So you should optimize the code also. You should perform that optimization also here. So these are the basics of the code design. First functional, second architectural, then hardware, software partitioning. In the partitioning, then do this hardware requirements, software requirements, do the implementation, finally integrate this. These are the steps involved in the hardware software code design. And it can be further classified into conversion of requirements and specification. We already told that take the requirement, convert it into architectural diagram. How it is possible? For that one we need some steps. First we should find the state diagram. From the date, DAG should be formed. Based on everything, you need to analyze it with the system flow diagram. You must know the flow diagram. You must need the pre-request. What are the pre-requests? How the components are connected? From which component to next component is connected? Everything must be there. All the things must be implemented by using the flow diagrams or system flow diagrams. So that is what called as the core specification. Developing system specification that describes the hardware, software, modules, relationship everywhere, everything. This specifications or synthesis. Synthesis means what are the hardware parts required for this particular specification. That one is identified and finally it is verified. Before going to all these steps, first the flow must be indicated by the flow graph. Then only you go for the hardware as well as software design. And during the design phases, each and every time integrate the code and check whether it is performing well, that is whether it is doing the correct job or not. Finally only you should develop the prototype. You should develop the system. First develop the model and develop the actual system. So first one is the in the hardware software partitioning. First introduces the system partitioning. The system partitioning, we need the design methodology. So many types of design methodologies are there. After that only it's divided into tasks. First you design a system for the entire process. Then that is divided into sub tasks. Then for each and every task you write the code. Finally integrate the code with the particular task. After that integrate all the codes to perform the system in a well manner. Okay. Then we'll consider this thermostat example. What is our task? Our main task is to measure the room temperature. That is our main task. So second one is compare it to the desired temperature. And third one is turn the heating or cooling based on it. So here for this embedded system, in my thermostat embedded system, I am going to design a thermostat. For my thermostat embedded system, I need three tasks. First one is measure the room temperature, that is task number one, and then compare the room temperature with the threshold temperature that is set by the user, that is the second step. And third step is turn the heating system or the cooling system based on the sub temperature. So three tasks are there. The three tasks are implemented in a separate manner. Room temperature measure. To measure the room temperature, first read the input. What is the input for this room temperature measurement? That is the temperature. So to read the temperature, automatically we need the sensor. So you should observe the value through the sensor, give that value, and the next step is compare the value. Sensor input is the analog input that must be converted into a digital input. So digitalization, digital input is there. In the digital input already I set my required threshold is 27. So my temperature is compared with 27. So it's always compared with 27. Consider now my temperature is 40, then it is compared to 27. After that the switch must be there. It will show whether you have to switch on. Switch will show whether you have to switch on this cooler or heater. So these are the basic things I need for this implementation. First measure the room temperature. For that one I am using this functional block. Second one is compare it into the desired temperature. So comparison, I need one block and a separate code is there to compare the value with the existing value. Then third thing is turn the heating system or the cooling system. So I need the switch or relay. That is my third thing. Based on that, I should switch on the cooler or heater. So these three are the compulsory things I needed to perform this particular task. So what are the hardware components required for this one? To read this one, I need the sensor. To process this one, I need the microcontroller. Then either cooler or heater. So temperature sensor must be there. Microcontroller should be there. There's a small processing unit to compare the temperature and switch on the cooling or heating component. And switch must be there to turn either heating or cooling. Or keep the switch as it is. So heating or cooling. For that one, we need the switch. Then remaining display is optional. If you want, you can display the current temperature. Otherwise, no need to display the current temperature. Some buttons must be there to operate it, to set the threshold. Suppose in my embedded system I want to change the threshold level, then I can use the switch to change the threshold level. So first three are the conditional components, that is it must be there for the design. Remaining two are the optional. Here we are not going for the heater or cooler. That is a separate embedded system. Here how to initiate. Our function is just to initiate the cooling operation or just to initiate the heating operation. That is our function. So what are the software requirements required for this one? First this is yes, ma'am. Hello? Whether my screen is visible to you?
Yes, ma'am.
Yes, ma'am. Okay, then software components. First, what is the first step? Code temperature sensor. So first get the value from the sensor, read the value. That is the first code. So first code required is okay. First one is code to read the temperature sensor. Second one is comparison. No? Compare the temperature. So code to compare the temperatures. Third one is switch on heater or cooler based on the temperature. So code to control the relay. Fourth is display information. If needed, use the display information, or if you needed, handle the button. These two are the optional. But these three are compulsory codes required for the implementation of this thermostat. Code to read the temperature, compare the temperature, control the relay. Okay, fine. Now we know what are the hardware component required as well as the software code required for this one. Now integrate these two. For this one, choosing the microcontroller, that is very, very important. We need the microcontroller. Based on the input only, you can select the microcontroller. Here the input is only one input, temperature sensor input only there. So only one port microcontroller is enough. A small microcontroller is enough for operating this one. So enough processor, identify the correct processor and take that particular microprocessor. Here, what all are our tasks? You take the input, output pins to connect the sensor and relay, and sometimes we may use the this switches also. In that case, use some more ports, and automatically we need to convert the analog temperature signal into a digital signal because we are comparing the values. Hence the microcontroller must automatically convert. All the microcontrollers can do that. It can convert the analog to digital. Conversion must also be there in the microcontroller. And second one is the optimizing software for hardware. Here a small code is there. If you more number of codes, then eliminate the, we can write the code step by step. Finally only we know that within three codes itself we can perform all the operations. So unwanted codes can be removed based on the memory usage. Here you consider the memory usage also. Here you want to store the input temperature, and similarly the threshold value must also be there in the register. You are going to compare these two things. If you want to compare these two things, already two registers must be there to for the comparison. So minimum two registers must be there. Based on that, you write the code. And the third one is interactions, how the register components are connected, how the registers are connected with this input code, and that is also important. That also you should know. So these are the overall steps required for this thermostat. So this part is called as the hardware software co-design in action. Now I simply told you read the value, compare the value, control the value, operate the relay. What is the first step? How it will be move to the next step? First nanocycle or first millicycle, the first value must be read out by the sensor, then that must be transferred, and then only you can get the code from the register and compare the code. Finally, based on the output, check whether it is higher or lower. If it is higher, switch on the cooler, or lower, switch on the heater. Everything must be confirmed. It should be done in a flow manner, that is one by one only. After each and every time duration only should perform all these operations, right? Hence we need the flow diagram. So system design patterns, these are the steps recorded in the system design pattern. First one is the state diagram, second one is the data flow graph, third one is the control data flow graph, and directed acyclic graph. From that only, after this only, you can fabricate this one in the silicon board. We know that I already told you what all are the operations: read the value, compare the value, and then finally switch on the relay. For that one, what are the states required? The state means what all are the functions that should be performed inside the embedded system. It can be defined in terms of states and flow graphs. What are the states required here? You can easily say that first one is idle. The system is in the idle, so we need one state called as the idle state. Okay, then if it is greater, that is compared by the code. If it is greater, the system will go to the heating state. It will go to the heating. Or if it is less, it will go to the cooling state. Another one is error state. These are the states required for this embedded system design, thermostat embedded system. First, the system is in the idle state. It's waiting for the input. Based on the input, either heating or cooling, one should be turned on at a time. That is important. The signal should not be given to the heater and cooler. So from this one, either this or this one is initiated. So in this diagram, this is what called as the pre-request. From this one, this is operated. And error, when will you see the error? If everything is wrong, suppose some malpractice is there, malfunctions are there, sorry, malfunction is there, it will transfer to the error state. So here there are three edges: edge A, edge A, edge B, and edge C. Based on the temperature, it will be operated. Edge A or B or C must be initiated. Okay, so here there are four states: idle state, heating state, cooling state, error state, and transitions, either idle to heating or idle to cooling. Or after, if the room temperature is constant, then it comes from heating to idle, similarly cooling to idle. Other than that, the error. So five transactions are there, five transfers between all the states. That is, first it is in the ideal. If it is increases, it go to heat. If the temperature is less, it goes to heating state. If the temperature is high, it will go to cooling state. Otherwise, if the temperature is okay, if it is in the threshold level, again it will in the ideal state. Or else, if the cooling also okay, fine, cooling is there, it will also in the same state. You know that now when you're operating AC and all, if the temperature is in the okay, fine, means it will be automatic AC, it will be in the same level only. Based on the environment, it will be automatically changed. So the next one is, first identify the states and the transitions. Second one is the directed acyclic graph. From this cycle only, you can identify which one is having the higher priority time, or higher time required for which task we need a long amount of time, and take that into consideration. For the embedded system, you should consider the longest time. So that based on that time only it must be designed. So the arrow here, this is example for the DAG. In the DAG, we know that the arrow represents the edges and this represents the nodes. So four states are there: A, B, C, and D. In this example also, four states are there: A to B, C, D. Here there is a connectivity between A to C. It indicates that there is the control flows from A to B as well as A to C or A to D based on some constraints, or based on some condition it may flow. In our example also we can write, no, first it's in the ideal state, either it may go to the cooling state or it may go to the heating state, or else it will go to the error state. So same manner it's designed, and in this example the highest value of edge is 10. 10 is the highest value of it. So for your embedded system, at least 10 milliseconds must be there for the entire operation. So this is the same one. Our nodes are temperature sensor, then compare, then control delay, display. This is the optional. Temperature sensors read the input. Edges are data flow from temperature sensor to the compare. That is one data flow. Another one is the result of comparison flows from the compare to the control relay. So this is the sensor. From sensor you will reach the compare. From that go to the control relay. And these are the main nodes used for this DAG. Okay. After identifying all these things, you just identify which path is having the higher value. That value is taken into account. And next step is that is the find the longest delay. Longest delay is taken, and that is used for the path calculation. Longest delay node is always consider for designing the embedded system. In addition that we will consider all these things: hardware, software, execution time. You should take account of this one during the design. Then hardware area required for design, amount of data transfer per minute or per second, and the execution order, data dependencies. All these things are taken into account before integrating the components. Take the task, decide that, and execute that. But before integration, you should take care of all these things. Okay, then how it can be partitioned, we will see in the next class. So after this only, you perform all the scheduling algorithms, find the particular task and do it. I'll explain it in the class. We'll see in the next class.